Yes, it's a very exciting session about the sustainable aviation fuel. And we start with a first presentation from Sasha Derry, with the CEO of Blue Shift Aerospace, a company developing a unique line of rocket powered by Bio-Derived fuel to launch tiny satellites into the space.
Sasha, I hope you can hear me. We've got the
Yes.
screen.
Sorry.
Okay. No
Okay,
problem.
much better.
Okay, over to you. Take it away.
Okay, my apologies. Had a little blip there. Well, thank you very much for the invitation. It's a pleasure to be here and a pleasure to share with you guys, everybody, what we're working on. We're very, let me just change my screen here so everything's good. We're very proud of what we were able to accomplish this year. So I'm the CEO of Blue Shift Aerospace. We've been around since 2014. We're based out of the state of Maine in the United States. And on January 31st of this year, we provided the first commercial launch of a rocket powered by a biofuel in the world. So I'd like to share a little video with you all. Hopefully the audio will come through.
5, 4, 3, 2, 1. Ignition sequence started. This is awesome. I'm so excited. This is fantastic. There are medium-sized companies and rockets that are launching, I would call them buses to space with medium-sized payloads, but we want to be the Uber to space.
So in our industry of launches, space launch, there's really a number of problems that our technology addresses. First of all, rockets are complex. They're expensive. They're inherently dangerous. And the vast majority of rockets that launch payloads, whether it's humans or commercial payload to space, they use toxic fuels and propellants. We're targeting a small satellite launch audience. And right now, that audience of folks, if you're going to launch a tiny satellite to space or a small payload to space, you really only have large carriers like the SpaceX's, United Launch Alliance, Virgin, and others. And that we're targeting an audience of these guys really don't have a way of providing dedicated launch services to take their tiny satellites to space. And what Blue Shift has invented is a tiny series of launch vehicles that use bio-derived fuel to provide a lower cost, environmentally sound way of taking these payloads to space. And because of our rocket technology, in addition to our non-toxic fuel, our rocket engines actually have half the plumbing associated with traditional liquid fuel rockets, which means we further reduce the cost of launching payloads to space. Now, many folks will ask us, what is your bio-derived fuel blend? Well, I can tell you this much. I can't carry, as you saw in the BBC video, I can't share with you what the exact formulation is. We got a number of grants from the Maine Technology Institute to develop the formulation, optimize the performance, and then a grant from NASA to develop a hybrid rocket engine to fully optimize the performance and stability of the rocket. And what you saw in that launch on January 31st was our first prototype launch of using that technology. Now, our fuel can be sourced from anywhere across the world. In fact, I discovered this fuel on my brother's farm here in the state of Maine. He has an organic farm. We were actually doing rocket engine tests with the petroleum fuel, and I sat down at his kitchen table, and just a week prior, he had pulled a certain substance that I saw in his kitchen, and I wondered, would it be feasible to use this fuel as a replacement for the petroleum fuel? And I thought this would be a fantastic story, a fantastic way to move for advanced space transportation. If this particular naturally derived source was even close to the performance that petroleum fuel provided. So about 2 weeks later, we constructed what we call a fuel grain or a fuel core for the engine, tested out the engine, and we found that the performance was superior to the petroleum derived fuel that we normally used. And then we also found out, this is certainly really unexpected, our fuel source is actually less expensive than the petroleum alternative. Our fuel is inherently very close to net carbon zero. The only sources of carbon is really transport, and then any sort of production costs in terms of refining the fuel. There's a little, if the energy used is not renewables, then there's some associated carbon creation. The fuel is inherently non-explosive, and unlike really any fuel, even bio-derived fuels, our fuel is completely non-toxic. So that means when we launch rockets over the ocean, we won't, if our rocket happens to ditch into the ocean, we will not be contaminating the fisheries and lobsters that our state is so reliant upon, especially our coastal industries. And you really can't say this about any other fuel. If whether it's a car or rockets, liquid fuels all too often are highly toxic, or at least partially toxic, to wildlife and ecosystems. And as I mentioned too before, this is inherently less costly than traditional rocket fuel, which is a version of kerosene, which is called RP1. It also happens to be more energy dense, so that means more calories can be retrieved from the fuel per kilogram or per cubic centimeter than traditional liquid rocket fuel. So there's a number of advantages. And then last but not least, we find that there's an inherent logistical advantage because of this non-explosive nature, its non-toxic nature, is low cost. It really lowers the cost for us to do engine tests, to produce the rockets, to safely go about the business of developing the rockets. And then ultimately, it'll really reduce the cost of transporting our rockets across the roadways of the United States, and then reduce our insurance costs when we ultimately launch these rockets from off the coast of Maine. So it's really an exciting time for us. We are the only company to date that has successfully launched a rocket using bio-derived fuel. And I believe we may actually be the first company, and maybe the only company in the near future, who will be doing one using a bio-derived fuel that is completely non-toxic to organisms. So with that, I'm going to pause and take questions from the audience. I apologize. I've only had one cup of coffee this morning. It is early morning here, and I am still waking up. Or early morning for me.
With regards to asking a question to Sasha, there is the chat line. But if anybody would like to take the microphone, we would be happy to pass it to you. Please just indicate by the chat your name, and we will happily pass you the microphone. While we're maybe waiting for anybody to chat, Sasha,
Sure.
So this all began around on a kitchen table with a bright idea?
It was discovered at my brother's farm in the town called North Yarmouth, Maine, here in the United States. Yeah. And
where do you see it going? Where do you see it going from here, Sasha? Where do you see it going from here?
Sure, we are actually working with, we are targeting launching academic and civil research payloads to space. So initially, we will be launching these payloads suborbitally, which just simply means we'll be taking payloads up to 300, 400 kilometers, providing them a zero-G access to space, and then retrieving them as they come back to Earth safely in the ocean. We are already lining up customers. In fact, some of our first customers are young people across the globe using these little Lego-like technologies called X in the Box to do their own science experiments. These are students of all ages, from 10 years of age to 20, 25 years of age. But ultimately, we will be providing payload space. We're going to be providing up to 30 kilograms of payload space to not only these young researchers, but academic and civil researchers, which are trying to test out new technologies, new science in space. A lot of them will be funded by NASA Flight Opportunities Program. And then within about 4 to 5 years, we will be providing orbital launch services for tiny satellites, these CubeSats or nanosatellites. Maine is very similar to, I guess you mentioned the UK, but the UK has this ability, Scotland has ability, New Zealand has this ability, but no place else in the eastern seaboard of the US can you launch into polar orbit. And what we've learned through a market research study is that half of these tiny little satellites called CubeSats want to go into a polar orbit. Now, polar orbit simply means that instead of going around the Earth, as we would commonly think of satellites, these satellites are going around the poles of the Earth, north to south to north to south, doing things like Earth imaging, providing broadband communication services. And so Maine, because of it has a coastline that's facing due south with no houses or people or property over the ocean, we can inject these satellites safely into orbit, where you can't even do this in Cape Canaveral from Florida and Wallops. The only other places you can do it in the United States is California at a military base, which is very, very expensive and hard to use, and Alaska, which is extremely remote and not very cost competitive. So we plan to do that within about 4 to 5 years from now. And I believe we will be the only ones to do this with bio-derived fuel and do it one with a safe, non-toxic technology, and the only ones to do it at a very dedicated small payload level. Most rocket launches are using hundreds to thousands of kilograms when they launch. We're providing this at almost at a single payload level profitably. That was probably more than you asked for.
No, that was really good. There's a question in the chat there for you, Sasha. 2 questions, if you could maybe pick up on those.
Sure, and I apologize. I'm trying to expand the window so I can see the full chat. If you don't mind repeating.
Let me, of course.
Sure,
Which I'll read you both one after the other. Which kind of client would you target? You've maybe partially answered that already.
Sure.
What is the production capacity of the fuel? Is it enough to cover all launches?
That's a really good, so I'll answer the first question. So our target customer base is initially academics and civil researchers from across the globe. Primarily in the Americas, though we have already got interest from Africa and Europe already to be payload customers. But they are academic and civil in nature, and we do hope to broaden out to commercial customers or that want to provide broadband and Earth imaging abilities, as well as some deep space access ultimately. We will be launching ultimately to low Earth orbit and not directly to deep space. So the payload customers will have to have additional propulsion engines on board. In terms of fuel capacity, that's probably our toughest issue here. In my state of Maine, I've been reaching out to a number of production farms, let's call it that, and trying to see if there's sufficient production of this fuel to power our rockets. And even though they're small, we're going to be using, for every launch, we'll be using hundreds of kilograms of this fuel at a time. And it turns out it's going to be a challenge. So while I won't be able to initially source these fuels solely from my state of Maine, there will be no issue with for sourcing the mixture of fuels from here in the United States. I just might have to go across the state border to access more fuel. Hope that answered the question.
Okay, Sasha, I have one additional question, please. You mentioned that your fuel is cheaper than the reference today. So do you explore other applications? Because it's not frequent that the biofuel are cheaper than the market reference.
Yes, it's very unusual. So it's kind of inherent that there's very little processing that's required for our biofuel. Now, our fuel, to be clear, is a solid. So it's probably a little more akin to wood in that nature. You know, there's not so much processing. It's not wood, just to put it out there. But it's because of its low energy input to process, it means that the cost is inherently lower. However, there are not engines, like there isn't combustible, internal combustion engines that can fully make use of our fuel at this time. It certainly is feasible. I know there's been novel approaches to creating engines that you actually use things like wood. But I think that the opportunity here with our particular fuel is in the aerospace industry. I guess in theory you could use it for other forms of transport. It actually takes a bit to get it to combust, but once it combusts very, very, very well, and it stays non-explosive. So I know I didn't quite answer your question. That it's cheaper, but it's not applicable to so many other forms of transport at this time.
Okay, thank you again, Sasha. Now, Paul, I think it's the time to move to the other presentation from Freya. And Freya is coming from LanzaTech. She is Chief Sustainability and People Officer. So Freya, please.
Thank you very much. I will just share my screen. So hello, everybody. Good morning. I'm coming to you from Chicago in the United States. And as mentioned, I'm here from LanzaTech. I will just doubly make sure that I'm not muted and everyone can hear me. And hopefully you can see my screen. So I'm here to talk about a new way of sourcing fuels and a new way of thinking about carbon. When we think about where we're at today in terms of climate change, there's an overabundance of carbon in all the wrong places. And really, how we look at it at LanzaTech is that all carbon is precious and we need to keep it locked up, really keep it in the ground and find ways to use the carbon that we already need or use and use carbon where we must. When I say use carbon where we must, if we think about energy today, it can be carbon free, but we do need a source of carbon for chemicals and fuels. And so what we do at LanzaTech is we think about where the carbon in your fuels and chemicals comes from. And why that's important is because that will define our climate future. So the core of LanzaTech's technology is a technology called carbon recycling. Essentially, it is, if you think about making wine or beer, you think about fermentation. And what we do is instead of sugars and yeast, we use gases, so carbon-rich gases, and we use a bacteria, a biocatalyst, that eats carbon in the gases as part of its natural biology. What it does is it then grows and divides, and as a product of this growth, it makes ethanol. Where we've scaled that today is using industrial waste gases, so carbon monoxide, carbon dioxide, fed that to the bacteria, and it's produced ethanol and other products. We've also demonstrated this taking agricultural waste, so woody wastes from farming and so on, and municipal solid waste, so household waste, including unsorted, non-recyclable plastic wastes. We've gasified this using partner technology, which essentially means superheating it to create a gas stream, And then we fed that to our biocatalyst, and it does the same thing. It turns that gas, that waste carbon, into new products. If we think about the future, we could also utilize carbon in the atmosphere using direct air capture technology. Now, as you know, CO2 is kind of like a stone. There's no energy in it. So you need an additional source of energy to unlock the potential in that waste gas stream. And so with the advent of electrolysis and renewable electricity, we have a sustainable source of electricity to unlock the potential of CO2. And so this shows a broad spectrum of waste carbon that's abundant and available today and is low cost. And as I mentioned, with this, we can make fuels and chemicals. And if we just take ethanol as an example, we can blend ethanol into the road transport market, but we can also convert ethanol into a sustainable aviation fuel, which is what I'll focus on today. And then the chemical space, we can convert ethanol into ethylene and then convert it into things like polyesters, packaging, plastics, and so on. And so we have this waste carbon story where we can lock carbon in to new products. And when they reach the end of their useful life, they can go back into the system, be gasified, and the carbon, it becomes a new carbon or sort of a circular carbon economy. It sounds like science fiction, but it's real. This is a picture of our commercial site in China. We've made over 20 million gallons of ethanol, which is the equivalent of mitigating over 100,000 tons of CO2. So it's real and it's actually happening. We have additional plants in various stages of construction using these different waste carbon streams, agricultural wastes, industrial waste gases from refining, the steel industry, household waste, and so on. And if we could utilize all of the wastes around the world, so not focusing on these projects here, but all the agricultural waste and household waste, industrial waste gases, there's the potential to make around 2 trillion liters of ethanol. Now, you might think we don't need that much ethanol because we're trending towards electric vehicles. Why do we need ethanol? But this is where our process of alcohol to jet comes in. We see ethanol as a building block, as a substrate for the future. And I briefly mentioned conversion into chemicals, and here's a sort of example of making yarns, plastics, and also using that ethanol in products like perfumes and cleaning materials. But the focus today obviously is on sustainable aviation fuel. And ethanol can be a feedstock to make a drop-in sustainable aviation fuel and a diesel. So we can take any type of ethanol, sustainably sourced ethanol, and convert that through a process developed by the US Department of Energy Laboratory Pacific Northwest National Lab in the US. And we've been working with PNNL for a number of years on scaling this process till we got to a point in 2018 where we had enough ethanol converted into our synthetic paraffinic kerosene, SPK, to use in a transatlantic flight with Virgin Atlantic. And then we also did a secondary flight with All Nippon Airways, ANA, in 2019, a trans-Pacific flight. So we showed that this is possible. We went through the ASTM process. We could use it in a commercial flight. And this was taking ethanol that first started life as the emissions at a steel mill in China. So it's really showing that you can give carbon another lease of life to make something that would otherwise come fresh fossil from the ground. The reason ethanol is such an interesting feedstock is because it's a regional choice and you can be flexible to your locations around the world. So you could site an alcohol to jet facility in any location, and it could be and it could use the domestic feedstocks that are available. And in particular, as I mentioned, waste feedstocks make this a very attractive case for many. So economics is not just the only benefit, but there are many studies about sustainable aviation fuels and the benefits for the environment, in particular around carbon reductions. But we've also seen studies, and this in particular study was done by the National Research Council in Canada, which showed the sort of beyond carbon benefits from sustainable aviation fuel. And this was using LanzaJet's alcohol-to-jet fuel. Which showed lower contrail formation and reduction in soot particles. So overall, it really shows great benefits to the users and to the planet by focusing our our future in aviation on sustainable aviation fuels. LanzaTech's core technology is gas fermentation, and so the alcohol-to-jet scale-up side has now been spun out into a new company called LanzaJet with the expertise to focus on this commercialization. We have investors, strategic investors from the refining sector, trading and also the aviation sector with British Airways. And we're currently building our first demonstration plant with a grant from the US Department of Energy here in the United States. But we're really looking to build in the next 5 years 3 larger scale commercial facilities globally. The reason we like to think about the importance of sustainable aviation is we liken it to the importance of batteries in the EV market. This is really existential. The aviation sector needs to have a shift, and they need the volumes to make that shift. But unfortunately, they're not available today. And that's not because of technology blocks. And most people think that technology is the limiting factor. Getting new technologies to scale is a technological issue. It's actually to do with policy. And the reason it's very difficult to put steel in the ground at the moment for sustainable aviation fuel companies is because of challenges with investor certainty. And a lot of that stems from the policy landscape around the world for sustainable aviation fuels. Today, there are policy frameworks, there are definitions or criteria for funding and government grants and so on that are limited to technologies that were from 10 or 15 years ago, and they haven't caught up with innovation. So what we need to do, and what I implore everyone to think about, is how we can move forward and bring those volumes to market, because the aviation sector, as I mentioned, sustainable aviation fuel is existential. They need to get the volumes, and there's a lot of fuel that's needed. But until we have policies that are technology neutral, until we support all solutions, we're never going to get to the point where we have enough to satisfy that demand. And so I'll just leave you with this image. I was talking about flying carbon smart as the sort of title of my talk today. But really what I'd like you to take away from this is how you think about carbon and how to rethink how you think about carbon. You can capture it and use it. You can replace fossil fuels. You can replace fossil feedstocks for products that you might use. Then you can put it back into the cycle and lock it into a new carbon economy. And I'll stop there and open it up for any questions.
No question from the chat?
I see there's a question about the gasification technology. It's a good question. Gasification is key for unlocking the potential of those solid waste feedstocks. We partner with our customers, and so the gasification platform depends on who we're working with. So it's not always the same gasification technology that we use. We are partnering, as an example, in India with Anchor Scientific and working with them on gasifying agricultural wastes. But we've also partnered in the US with Inentech on gasifying other types of waste materials. So it depends on who we're working with. Production volumes of large-scale facilities. So our demonstration scale facility in the US is around 10 million gallons per annum, and we are in the sort of early stages of looking at building around 30 million gallon per annum commercial scale facilities in the next 5 years. The interesting point to mention there is that the funding through LanzaJet that we've secured with our investors is a commitment to build the commercial facilities once all the key performance indicators of the demonstration facility have been met. So this really shortens the time to get to commercial scale, rather than building the demo, seeing that it works, and then going back out to market to secure investors. And so we followed the model they use in the pharmaceutical industry to really shorten that time. The biocatalyst is a naturally occurring organism. It is one that we accessed from a bacteria library many years ago, and essentially it has evolved in the laboratory through natural selection. In terms of over a number of years, we've sort of run experiments to see if it thrived on certain gas streams in certain conditions, and so on. So it is a naturally occurring organism. We are also working on the ability of the organism to make other products, and have demonstrated over 50 products that would be a separate organism where we have understood more of the genetic changes within that. Lots of questions coming through, trying to keep up with all of them. Elaborate the cost and potential for reduction. So both of those depend on the feedstock and the geography where the technology is deployed. For example, it could be in a location where there are additional tax credits for using certain feedstocks, which will impact the overall cost. Again, that will impact the life cycle of the fuel itself as well, depending on grids of the location where the site is based, and so on. But in general, we are showing about a reduction of around 70% relative to fossil jet for our sustainable aviation fuel. Sorry, lots of questions. I can't quite keep up. I'm not quite sure I understand the life cycle question, but I should probably say we have third-party assessments done of our life cycle. We also work with the Roundtable on Sustainable Biomaterials to assess the holistic picture of our fuel, and we include many sustainability aspects within that. So question about the steel mill experiences. We're actually, so I showed you a picture of our commercial site in China. I didn't actually include a picture of our plant in Ghent. It is should be operating at the end of this year, the beginning of 2022. But that site is well underway. In fact, last week, I think on Twitter, there were some lovely video clips of our bioreactors being shipped and transported to our site in Belgium, where we will be converting steel mill emissions from the ArcelorMittal site in Ghent into ethanol. So that's very exciting and still going on. We don't have ISCC certification. That is something we would be working towards at the moment. We have been working primarily with the Roundtable on Sustainable Biomaterials. Our site in China, for example, was the first site in China to receive that certification, and the first carbon capture and utilization facility globally to receive that certification as well. I think I've got through all the questions, so I might stop there if that's all right.
Okay, thank you a lot, Freya, for this nice presentation. It's very clear. So now I propose to move this to Neville Airgrids, Vice President of Waste to Fuel in Velocis. He is also responsible of the commercial, financial, and corporate development of the Altato Waste to Fuel project in UK.
Thank you, Michael. Now I'm going to try and share my screen. There we are. Good. Well, good afternoon, everybody. Thank you very much for coming to this this session on sustainable fuels. We have a different technology approach from LanzaTech, but fundamentally we too are looking to make sustainable fuels from waste materials and make better use of carbon. I'm going to focus mostly on our project in the UK, which is called Altalto, in partnership with British Airways. But first of all, I'll tell you a little bit about Velocis, my company. So we've been around for nearly 20 years. We're a collaboration between a spin out from the University of Oxford in the UK and one from the Pacific Northwest National Laboratory in the United States. Those two put together a technology for synthesizing hydrocarbons, which are the building blocks of fuels, using a catalyst and a reactor that are our proprietary design. And you can see a picture of the reactor at the third from the left at the bottom there. That's a full-scale commercial reactor. And on the left, you see both the insides of it and also the catalyst that we use. We've built up our knowledge over many years and created a substantial amount of intellectual property, and that's really around one step in the conversion process. But what really interests people is to be able to transform waste materials into useful fuels. And so we've partnered with other technology providers, and I'll explain our process flow in just a minute, to create that end-to-end solution. So taking a variety of carbon-containing materials and making them into fuels. So we supply our technology to third parties. There's a company called Red Rock Biofuels in the United States that is using our technology, but we're also developing two projects of our own. One in the United States based on woody biomass. So these are the residues from forestry, things like bark, the young trees that get removed to give the bigger trees room to grow, and the chippings and sawdust. So the waste materials from the forestry industry. And the project that I'm involved with, which is using municipal solid waste. So Altalto is the name of our UK project, and it's planned to be the first waste to jet fuel plant in Europe, taking about 500,000 tons of ordinary black bag waste, the stuff that can't be recycled. It's mixed up and it hasn't been segregated. And so it would end up, if we didn't take it, it would end up either in landfill or be incinerated, burnt with some energy recovery in the form of electricity. But that's a really bad way of using that carbon. It creates a very high carbon electricity, and it's a very inefficient process. Whereas if we can take that carbon and instead make it into sustainable aviation fuel, back out ordinary fossil jet fuel, then we're really achieving something in an industry that is extremely difficult to decarbonize. So this is the process scheme that I mentioned before. And as I said, we partnered with a number of technology licenses for the different parts of this process. We went through an extensive selection process over many years to select licenses that had sufficiently well demonstrated technologies. Because in order to finance a project like this, we need to be working with technologies that have sufficient level of provenness. Now, some of the technologies in this scheme have been around for many, many years. So, for example, on the right, Haldotopsa is a very well-respected supplier of all sorts of refinery technologies, and their hydrocracking technology has been used in hundreds of different installations. On the other hand, the gasification, the Syngas Generation, the second step in this process, and the Fischer-Tropsch synthesis, which is the bit that we supply, they're much more novel technologies. So, but each of those has been demonstrated at commercial scale. And so we're putting together this scheme and coordinating the whole thing with the support of Worley, one of the world's major engineering contractors. And so this scheme takes residual waste. It does some physical conditioning, removal of things like metals and stones, inerts. So then we have a conditioned feedstock that's suitable for chemical processing. The Syngas Generation is essentially a gasification reaction, makes carbon monoxide and hydrogen. That's which is known as syngas. That syngas needs to be cleaned, remove any contaminants, and make it ready for the synthesis of hydrocarbons. Now, one of the interesting things about preparation of that syngas is that in the course of that, we actually make a side stream of concentrated carbon dioxide. And that is important because it gives us the opportunity to sequester it and use carbon capture and storage, which allows us to make negative carbon fuels. So without carbon capture and storage, we can achieve perhaps a 70% reduction in net carbon emissions across the life cycle. With carbon capture and storage, it's well over 100%. And that's very important because we really need to find ways of getting the whole industry to net zero. So we need some technologies that take us below zero. The fuel that we make, it's very similar to jet fuel. It's called synthesized paraffinic kerosene. Both the route that we follow and the one that LanzaTech follows have been approved by the ASTM, the American Society of Testing Materials, which is really the defining standards body for jet fuel. And it can be used in existing engines without any modifications, so it's ready for use today. And this is really important in aviation. Some of the, you see some news items about electric planes, hydrogen planes. These have two major limitations. One is that they're not really suitable for long-haul flight, only for short distances, and the other is that they're not ready today. They need substantial testing in flight before, and substantial investment in aircraft and infrastructure before they could become a significant part of the industry. Whereas sustainable aviation fuel can be used today, and it also, as well as being lower life cycle carbon dioxide emissions, it also burns more cleanly than conventional fuels. So the picture you see there is actually diesel, not jet, but they're close cousins. And you see the difference. The soot, the particulate matter that is produced by conventional fuel is pretty much absent from our fuel, as is the sulfur. And so you get a much improved air quality. Just a little bit about our project to put it in a bit of context. So it's located in Immingham on the east coast of the United Kingdom, with, as I said, ourselves and British Airways as the investors, where our main product is synthetic paraffinic kerosene, but we also make some naphtha, which is blended into gasoline, petrol. And this plant will produce about 20 million gallons per year of product, from something between 500,000 and 600,000 tons of municipal solid waste and commercial and industrial waste. And as I said, potential for more than 100% CO2 savings. And we, all being well, we hope to have it in production by 2025. But as Freya mentioned earlier, policy is crucial to the rollout of these sorts of technologies, and I'll come on to that in just a moment. So this is a picture of the site with the 3D model of the plant on it. I guess the most important points on this are, first of all, that we've got planning consent. That's a very important piece of permitting for any project. And secondly, that we're physically close to the local carbon capture and storage cluster. Now, as we think about how sustainable aviation fuel is going to fulfill to take the place of conventional jet fuel, there are really 3 generations of it. And I'm borrowing here from a report done by the World Economic Forum last year. The first generation is in use today, which is based on waste and residue lipids, essentially fats and oil, naturally occurring fats and oils. And that's what's known as the HEFA route, which is relatively low cost conversion, but it's limited by volume. There isn't enough of that feedstock to meet the demand for jet fuel. Whereas the second generation, where we're using solid waste materials, a much broader set of feedstocks, that is the one that is really going to enable us to decarbonize the whole industry. And the 2 main technologies that allow us to do this are gasification Fischer-Tropsch, which is what we're using, and alcohol to jet, which is what LanzaTech is using. There are some other technologies that may be helpful as well, but those 2 are likely to be the 2 main routes. And then the third generation shifts to capturing carbon from the atmosphere. So using direct air capture and again, Fischer-Tropsch synthesis to make hydrocarbons from that. And that gives us potentially access to an unlimited source of carbon feedstock, but without energy content. So you have to supply renewable energy to make that work. And so just want to close on a policy note. Those second and third generations of sustainable aviation fuel are absolutely essential if we're to deliver the volume we need. And development of projects such as ours depends absolutely on the regulatory framework. The UK has a thing called the Renewable Transport Fuel Obligation, which is quite a helpful foundation, but it doesn't really do what's necessary to enable plants to be financed. We're seeking a mechanism to give some price stability, rather akin to how it worked in the electricity industry in the UK with the contracts for difference. And we believe that with something like that in place, not only we, but others in the industry can really start to build this out and make an impact, a significant impact this decade in decarbonising aviation. So I think I'd like to close there and take any questions. Stop sharing so I can see anything in the chat. So there's a question about if we use plastic waste, are we releasing fossil carbon into the atmosphere? Yes, we are. But the thing is, what else are you going to do with it? Today, the alternate really landfill is no longer a serious option for all sorts of reasons, including the leaching of materials. And just the availability of space. So what else happens to this stuff is it gets burnt inefficiently to produce electricity, which we could actually make far more effectively using wind power or solar power. So there is a net greenhouse gas benefit, yes, there is, in turning this into fossil fuel, into aviation fuel. And of course, if we can do carbon capture and storage as well, which we certainly can in the place we're targeting, then there's a very big benefit. Okay, I don't see any further questions. Michael, back to you if you like.
Yes, I have just one question for you, Neville. You mentioned that it's very important and mandatory to have regulatory mandates because the cost of production, of course, is higher than the fossil jet price. Do you have an order of magnitude of the gap between your production cost and the jet market price today?
It's quite substantial. So I think I'm not going to give our own figures specifically, but the industry is typically talking about maybe 3 times for heifer, the first generation, and perhaps 4 to 6 times for the second generation. Now, I would emphasize though that these are first of a kind plants. So what if you think about the cost of producing jet fuel back in 1890 or something like that, when it was first being dug out of the ground, there's been very substantial improvements in cost effectiveness over the century or so that petroleum's been in use. So I think we can expect a fairly rapid reduction, but it's always going to be more expensive than conventional jet fuel because that is a uniquely convenient energy source. So a couple more questions. What preparation is required for MSW? We actually will take it without any preparation. We do the preparation on the site. And does your economic need to phase out generation biofuels? Can add the other forces? That's a really good and interesting question. So we don't see ourselves being the cause to phase out first generation biofuels. So long as they provide a greenhouse gas benefit, they're performing valuable work. It's just that first generation can't. Well, so I'll make a distinction between first generation SAF and first generation biofuels as a whole. So ethanol, biodiesel, they have their part to play. In first generation SAF also has its part to play, but it's not going to be replaced by our technology. It's going to be augmented by it. The main problem with it is there isn't enough of it. And have we thought about using other organic waste? Actually, we do. Yes. So the waste we take is not segregated or selected in any way. It's everything that people throw in their rubbish. So it includes food, cardboard, textiles, plastics, everything that's mixed up. Do I think multipliers are necessary? And we mentioned regulatory framework. Which other European countries? Well, I mean, there is the Commission is presently working on a policy for mandating sustainable aviation fuel across Europe. We're not yet sure whether that will provide the necessary framework, but it certainly is a starting point. I think there's kind of a general recognition that the aviation industry has to tackle decarbonisation now, and so whilst there are some variations globally as to how that gets done, I think there's a clear direction of putting in place policies that support the investment. The issue for us is we need to do it quickly. There's an awful lot of decarbonisation to be done. It takes time to put these plants in place. We want it to happen now. Okay, that seems like the questions have dried up. Michael, can I hand back to you?
Yes, thank you. Thank you again for this presentation. And again, it was a very three interesting discussion about the opportunity to develop SAF and the highlight of the requirement for legislation obligation to support the SAF development, and also to cover the risk taken by the technology developer and the operator, as well as the future of taker. So for now, I think we are close to the break. If you want to add something on conclude.
Yes, Michael, thank you very much. So Neville and Freya, thank you very much for your contributions. We understand you now have to attend a meeting outside of the Bio360, and we would be delighted to welcome you back at 4:30 if your meeting is already terminated by then. So to all our participants, thank you for taking part. We're now going to take a half-hour break. We suggest you just put the session on pause or leave it running. We will put the meeting on hold, so you stay on the same link, and we look forward to welcoming you back in half an hour for 3 more interesting presentations on sustainable aviation fuels. Thank you very much. See you again soon. So, welcome back, everybody. We hope you've had a nice coffee break. And now we start the second session of our focus on sustainable aviation fuels. And we continue along the path of exploring the diverse range of biomass feedstocks that are available and how they can be valorized in terms of producing sustainable aviation fuel. So Michael, I would like to pass the floor to you and you can introduce our next speaker. Thank you.
Okay, thank you, Paul. So the next speaker is Bernhard Karlsson from ST1 Sweden. He is a Director of Public Affairs and Renewable Energy. He has a long experience in oil industry, in Shell, but also in ST1. So Bernhard, please. You are on mute.
Can you hear me now?
Yes, okay.
Okay. Okay, good afternoon, everybody. My name is Per-Arne Karlsson, and I work at ST1 as Director for Public Affairs. My company, ST1, is, let me see if I can just, I have some problems with shifting these slides now. Okay. Sorry for that. I probably need to take my headphones off and shift it if it's okay. I'll try that.
Maybe try opening and closing the file and starting again.
Yeah, let me try that one. Can you hear me now? Yeah. Can you hear me?
Yes.
Okay, I probably need to be outside my headphones. Is that okay for you?
I think so. It's the translators which need to respond. Can you speak so that the translators can hear
Yeah,
if the sound is okay?
can you hear me so can you hear me so I can be outside my headphones? Yeah. Can they say something?
They've said that it's better with a headset if possible.
Yeah.
Is it...
Yeah. Okay. Let's try it again because it's.
Well,
Anne, if you like, we can take over the presentation. We have the presentation. We can show the presentation, and you just have to tell me when to put the next slide. Shall we do that?
Yeah, I have changed a little bit to it, but I can maybe can I have it in not presentation mode, or can I? Yeah,
it's better if we have full screen.
So yeah, it didn't work to shift it, but let me try then. Yeah, now it works. Okay, so coming back now. So sorry for that technical problem, but my name is Per-Arne Karlsson. I work as Director for Public Affairs in ST1. ST1 is a Nordic energy company. We have a vision to be a leading producer and seller of CO2-aware energy. And of course, everybody is in that sector more or less today. And leading for us is not being the biggest, but being in the front line of developing new techniques in terms of different transport, aviation, and marine fuels, and also in carbon capture. We would like to be in the value chain, both of producing and selling the energy. I will take us a little bit back and set the scene for my rest of my presentation. Why are we where we are? We can see here an illustration of the Mount Everest, as we call it. We have climbed the Mount Everest the last 100 years, quite steep up in the transition to be where we are today. We have actually used fossil fuels, and the industry has developed in a way that we all have benefited a lot from, but we also can see that that had costed a lot in the climate impact and the climate change that we can see today. In order to make that happen, going back a little bit and take us back to a better pathway in the future for us and for our children, of course, we need to climb down this mountain, and we need to do it a little bit quicker than we have done the up climbing. A lot of these measures that we can see that are available is, of course, renewable energy, and that goes very much into the aviation sector and sustainable aviation fuels. Energy efficiency, which also talks about a lot of what will happen with the technique around the airplanes, but also energy efficiency in general in society and how we use the energy. And then we as a company very much talk about carbon capture and carbon capture utilization as well. And I will come back to that a little bit at the end of the presentation, where we also can see some of the future fuels being available for the aviation sector. We need also to combine this with carbon sinks and afforestation and planting new forest, because we can also see we have a lot of excess CO2 already in the atmosphere. So not only to balance and be better to what we do today, we need to look at what we have done and remove a little bit of that. I will look on the distillation curve challenge, as we call it. We have a refinery in Gothenburg. If you look at the distillation column at the left hand of this picture, you can see in the middle jet fuel, about 9%. If you have a configuration of a refinery and you need to produce fossil jet fuel, which we today need to do a lot, because we have, not maybe today in the corona, but normally we have a lot of aviation going on in the world, and we need jet fuel around it. As long as we need jet fuel and we produce that in a normal refinery, we get only about 9 to 12% of the jet fuel out there. And that means that we have the rest, 88 to 90%, is other products that we need to place somewhere else in the world. They will probably, at worst case, be burned. So therefore, having said that, it's really, really important to really change the molecules from fossil jet fuel into other energy sources, like aviation biofuels, or maybe energy as well. As we know, electricity and electrification of the aviation sector is quite hard, and it will take some time before we have even a lot of it. I can say that in Sweden, we can probably see in 3-4 times when the years when I travel from Stockholm to Gothenburg, I will probably do that by an electrical plane now and then. But when I go from Stockholm into other cities in Europe, that will probably take a long time. And going across the Atlantic, probably even longer. And I don't know even if that will happen. So therefore, the segment of aviation need to be replaced with biofuels the quicker the soonest as we can do that, and therefore it's also competing with the rest of the transport sector very, very heavily, as I will show later on. If you look at Europe, this is a couple of years ago, 1.5 years ago, we looked at the mandates in Europe, and this is mandates outside aviation. What we can see now is that aviation mandates is coming into place. In Sweden, we will from 1st of August have a reduction quota starting up for aviation sector. Norway started last year, and we have some other countries in Europe starting up. So this figure that you can see here, 22 million cubic meters of HVO needed for the transport sector mandates, that will be even higher. We can also see now in the Green Deal and the RED II revision and the target setting we are going from 40 to 55%, we are going for Fit 55. That will also increase the targets for many, many countries. So this figure is probably much too low. And if we then look at the production of how much HVO are we really producing in the world, we can see that this figure will grow a little bit. We can probably come up to 15 million cubic meters in the global potential of HVO production in a couple of years. But still, as you saw on the other slide, there will be a gap, and there will be a lack of biofuels and HVO in this sector. And therefore, I come back to what I started to say a couple of minutes ago. There will be competition on where to put these molecules and these biofuels. As you saw in my distillation curve challenge, we think very, very heavily that we need to have biofuels in the aviation sector by real molecules in order to get control over the distillation curve challenge, and by that also limit the fossil fuel production going forward, because the overall climate change is very much about limiting the fossil fuel production. So with this environment as a background, it was not so difficult for our board to take a decision to invest in Gothenburg. Our refinery in Gothenburg is a normal middle distillate refinery, but we are committed to transfer that into a renewable refinery in many, many different ways. We are looking at feeding it with a bio crude instead of fossil crude, and we are also looking into build units on the premises of where the refinery is. This green processing unit investment we started a couple of years ago. It's about 2 billion Swedish kronor that we are investing in this unit, and it will be up and running, hopefully, end of 2022. There are some time constraints due to COVID because we have some international cooperations around the technique and how we do the investment, but it's going on schedule for the moment. As raw material here, we have a flexible setup, but we will have approximately half of the raw material will be tall oil, and almost all of that will come from SCA, the Swedish forest company. But we will have some imported tall oil as well in order to come up to these 100 KT. Then otherwise it will be vegetable oils and animal fats that we will use in this setup. The outcome of the production will be approximately 200 KT per annum, and it can be divided between HVO for transport sector and also into biojet for aviation sector. This technique setup gives us a limitation of about maximum 75 KT biojet. So we have a limitation in how we have built this and construct this, but in order to be able to put the best needed molecules on the market, we have built it flexible anyway. We can also do, of course, 100% transport HVO, but and we can also run it on fossil raw materials if that is needed in the circumstances. But of course, that is not at all what we want to do. We will definitely come up with this as a renewable unit and start to run it that way. If you look in Power to X and other future solutions in this sector, you can see in this picture that, again, coming back to quite tough targets. If we talk about the Nordics, the targets we have set today in the Nordics, and again, that's without the aviation mandates that will come into play in Sweden, and that has started in Norway very, very small scale. We need up to 8 million cubes of low carbon liquid fuels only in the road transport sector. If you look at the picture on the left-hand side, you can see our view of this. We think electrification will be needed and definitely the best measure in the short range distance, and maybe if you go on the small cars. There will be a change coming quite quickly towards 2030 in this, but the more left you come on this picture down here, the more difficult it will be to electrify and to use electrification as the one and only measure. On the left-hand side, you can see aviation. Again, what I said earlier, this is a very difficult sector to electrify, and therefore, repeat it again, we need to put some biofuels and liquid fuels into this. It can be biofuels, it can be future, it can be hydrogen as a solution, and other also liquid fuels that I come back to. In the e-fuel sector that I will describe a little bit more on the next page, we can see synthetic fuels, we can see electrofuels, and we can see a different kind of techniques coming to evolve after maybe 2025 and onwards. Today, we have an issue and a challenge to really scale that up and to have control over the cost in the whole process. But there will be definitely technique development coming very, very soon and around the corner, both in terms of e-methane, e-methanol, and other electrical fuels, but also in general, we can use that in the aviation sector. The current electricity network in the Nordics, and I should say it's more or less the same in the Europe. We need a lot of green electricity for these electrofuels and the synthetic fuels if they should be able to also help with the lack of biofuels going forward. So we need to build and ramp up a lot of renewable electricity production capacity. In Sweden, we are building a lot of windmills. We are getting better and better on solar power, but we need also to look over the infrastructure. We have some very, very narrow parts of the electricity grid in Sweden. So we have actually some transport issues around there. And going forward in Europe, I think we should look at cross-national, cross-border transfer lines, and so we can actually use the green electricity that will be produced in a much wider range than we see today. It also a lot of regulation that needs to be in place. How do we measure the electricity used for e-fuels, for example? How do we calculate the CO2 emissions? Do we need really to have all the regulations in place at day one, or could we put some phased approach to some of the EU regulations? We can see that in the Green Deal now, the RED II, the directive is up in the air, and a lot of things is discussed. And it was actually a consultation meeting yesterday where we discussed a lot of the RED II public consultation and how it should go forward. And you can see a lot of unclarity on how this will actually go forward the coming 4 to 5 months. So I will bring this picture to the full first. If you look at this picture and imagine the end game, whenever is the end game? Yeah, who knows that? We hopefully think that it will continue a long time with all these type of development, and it will be a transition, definitely. 2030 is a year, not an end game. 2045 is a target year for Sweden, for example. We will see biofuels as one part in HVO and SAF, but there is limited feedstock resources, as I mentioned. Biogas will come into play, but maybe not so much for aviation, but it will be for heavy duty, and it will help then to free up biofuels for the aviation sector. Solid biomass, yeah, we are looking into that. It can be ethanol, it can be alcohol to jet, and those type of techniques. But we struggle a lot with having these as a competitive solution for the moment. Then we have the electrification that will help in many of these different areas and also in aviation. But it must be a balanced solution between direct and indirect electrification here. And on top of that, we can see hydrogen, e-fuels, and e-gases. So when will this come? When will they become profitable? How do you do business in the transition period? That is the question for us as a company. And finally, my last slide is about what are we planning to do. This is no investment decisions. This is no board decisions taken, but this is what we discuss for the moment. You saw our GPU1, but we are already discussing a GPU2 with double up capacity. Can be from vegetable oils, but it can also be solid biomass if we come to solve that solution. This time we will build it fully flexible, so we can do 400 KT or cubic meters of aviation fuel if that is what the market is needed. We have a planned cooperation unit on 300,000 metric tons, which will be more of MOGAS components and maybe HVO, but as it is in black, it's not, in my view, so much for the aviation sector here. So ethanol from solid biomass, we can see, and this is beyond 2027, 2 to 4, 40 to 50, 60,000 metric ton plants doing ethanol. And as I said, alcohol to jet can be a solution for the aviation sector. And we are in some other projects also that is about to start, that is partnerships and not our own project. We are looking on an overall gas strategy, and hydrogen is here, one solution. Hydrogen, again, is like electricity. It can be an ingredient in electrofuels. It can be a own energy carrier. And we also need it definitely in the refinery process when we are processing our raw materials. So we need green hydrogen going forward. Biogas, mainly for heavy duty. And then we have carbon sequestrations program. As I mentioned in the beginning, we need to also remove CO2 from the atmosphere. We will come through with a couple of quite big projects in a couple of months about nature-based solution. It's mainly about afforestation and planting forest in some areas. Direct air capture will come, but that is more a solution for doing electrofuels indirect to aviation sector. And then, of course, market programs and how we in this transition period can help each other to do reduction from the atmosphere, and by that way, reduce CO2. But it's important in this sector, and that's sometimes discussed in aviation as well. We should not compensate. We should reduce, and we should make sure that we do this for real, so we come towards a zero emission future. That was all from me. Thank you.
Thanks a lot, Bernard. Please feel free to address your question through the chat.
Yeah. So let me see. We have.
So Per-Arne, your point is the picture is not clear today. You have a multiple solution
Yes.
for various challenges, and you have to adapt day to day with a long-term vision. So this is difficult, but up to now in ST1, you are developing your strategy to match with the net zero objective.
We think as I said, the aviation sector needs to be fulfilled for real, because we have this distillation curve challenge, which is also giving the opportunity to reduce the fossil fuels for real, which is the overall one target, and where aviation. Otherwise, aviation sector, for example, it's if you talk CO2 emissions, it's probably only 3 to 4% of the global CO2 emissions, but there is, as I said, other challenges, and therefore we will definitely put some effort into producing, as you saw from the beginning, maybe at least 300 to 500 KT aviation fuel, and then going forward with different new techniques for that.
Okay, clear. So I don't see any questions through the threads, but it's not. Doesn't matter. We have the opportunity to have extended discussion at the end of the session. So I propose to switch to the video presentation from Steve Mark Kurgels, with the CEO of Agricultural Waste Solution, a company looking for added value for SAF production from the animal manure.
Co-product of producing biochar from dairy manure. That's me in the upper right photo explaining the biofuel production process to a group of visitors. The upper left photo shows the Scott Brothers Dairy Farm in Southern California, our current host site for biochar and biofuels production. Scott Brothers milks about 1,100 Holsteins and farms about 700 acres of land for animal feed. The lower left photo shows the AWS microbial refinery at Scott Brothers with the pyrolysis unit on the right, the biofuels production unit in the middle, and part of the water treatment system on the left. The lower right photo shows the carbon negative biochar and Fischer-Tropsch products. Fischer-Tropsch, or FT, is the type of process we use to create the jet fuel. And you'll note how clear and clean the FT diesel fuel is in the photos on the left in comparison to the petroleum diesel fuel on the right. FT diesel or jet fuel properly produced is always of the same high quality, regardless of the feedstock. And dairy manure is an exceptionally good feedstock for producing FT jet fuel, the cleanest burning jet fuel on the planet, because it's very consistent in its chemical makeup from day to day on dairies that have a nutritionist who controls the animal's diet. Next slide, please. This shows the AWS milestone history. I'm only going to mention some of the bolded items, starting with 2009 and obtaining the first full operating permit for biomass pyrolysis from the South Coast Air Quality Management District in Southern California, well recognized as one of the, if not the most stringent air district in the world. It's relatively simple to obtain an R&D permit from South Coast or from the San Joaquin Valley Air District in the Central Valley of California, but obtaining a full commercial operating permit is extremely difficult in these two air districts. In 2013, we obtained the first South Coast permits for manure pyrolysis plus biofuels production and enabled 26 dairies in the Western Riverside County Ag Coalition to renew their CAFO operating permits for another 5 years. In 2015, we produced the first ever sulfur-free Fischer-Tropsch or FT diesel and jet fuel from manure. And in 2016, we were invited to the White House to accept an EPA Nutrient Recycling Challenge Award for our work with manure-derived biochar and biofuels. In 2021, we will commercialize our carbon regeneration center and microbial refinery model for jet fuel and biochar production. Next slide, please. The major issue and opportunity we want to focus on today is that of the fact that aviation and agriculture together contribute about 13% of global greenhouse gas emissions. Biochar is certainly a viable solution for the ag part, and I'm not going to be talking about the biochar part today. However, biochar production is expensive when the co-products produced are of low or no value from the roughly 50% of the carbon that is still contained in the syngas of biochar production. Aviation in general as an industry has a huge issue in reducing their carbon footprint. So aviation travel emits the highest greenhouse gas emissions per passenger mile of any form of travel. It's about 4 times that of automobile travel. Serious ozone damage can occur at the higher altitudes due to the sulfur in the jet fuel, plus the aerosol formation from the jet engine designs. This is one of the reasons, or one of the concerns, that grounded the Concorde fleet of jets traveling at very high altitudes and supersonic speeds. The aviation industry really has no way to reasonably obtain carbon neutrality by 2050. They're not going to go to electric or hydrogen planes, probably in our lifetime, not the big aircraft anyway. And so they're somewhat unique in that they don't have any way to achieve carbon neutrality except for carbon negative jet fuel. So that's really what we're talking about here, comparing it to desulfurizing petroleum jet fuel, which actually increases CO2 equivalent emissions. Petroleum jet fuel refineries really can't meet the emission standards in California and increasingly in other regions without carbon offsets. So a viable solution is to regenerate carbon emissions from a high greenhouse gas emissions feedstock, like manure, it's one of the highest in the world, into carbon negative jet fuel and biochar. So we plan to utilize next generation graphene-based technologies to economically produce the lowest carbon intensity jet fuel and the resulting highest low carbon fuel standards, LCFS credits here in California, at the lowest possible cost, resulting in the highest value co-product of producing biochar. Next slide. This slide shows the AWS carbon regeneration cycle on a dairy farm. I'll just spend a minute on this. At position 1 at the top, you see the cows feeding on the food crops partially grown on the farm using manure-derived biochar. Going around the cycle clockwise, the cows excrete the manure. The liquids are separated from the solids. The solids are fed into the pyrolysis system to produce biochar and biosyngas. The syngas is conditioned to produce the jet fuel and parasitic power for the site. The conditioned syngas is converted into sulfur-free jet fuel and or diesel fuel and wax. And the liquid diesel fuel can power the farm equipment that harvests the crops grown with the biochar. The wax is sold to an FAA-certified jet fuel refinery for the final refining and FAA certification process. And then the closed-loop zero-waste carbon regeneration cycle begins again. Next slide. This slide shows the basic inputs and outputs of each stage of the AWS process, as well as the product and profit options. I'm not going to go through the inputs and outputs, but instead let's look at this blue box entitled Multiple Carbon Negative Product and Profit Options. The first point is that the nutrient-rich biochar, manure biochar, plus the jet fuel provides profit flexibility with market variations for the two main products. I should point out here that our primary products of biochar and jet fuel in the form of wax have indefinite shelf lives, a major advantage in balancing production versus inventory forecast, especially for our offtake partners. The process also produces fertigation water, potable water if needed, and parasitic power for the system, all of which reduce the carbon footprint of the operation by reducing or eliminating the external purchases and carbon. The process can also convert anaerobic digester biogas, landfill gas, or any type of flare gas into jet fuel. The system can work alongside of a digester. I think Shannon mentioned this as well, to convert the greater than 50% of the manure carbon that remains in the digestate into biochar and jet fuel, converting the digestate liability into revenues and profits. Dairies that are too far remote from the major gas and electricity grid backbones of the networks to sell their biogas or electricity to the utilities, which constitutes most of the dairies in California and elsewhere, can easily transport the jet fuel and biochar products to market without depending on the utility companies. Projects scale up by adding portable, standardized modules operating in parallel, either on a single site or dispersed amongst several sites. You can see that our project financial goal is to have an earnings before income and taxes, return on capital employed, which is called ROCE, of greater than 20%. Next slide, please. So I'm going to quickly review how high greenhouse gas emission feedstocks like dairy manure can be converted into high low carbon fuel standard credits for the carbon negative transportation fuel. So this slide shows the 20% CI reduction, carbon intensity reduction target for fuels in California by 2030. The standard pathway and carbon intensity is set for each type of fuel, and the state does this, CARB does this, California Air Resources Board, depending on its life cycle, what they call well to wheels for transportation fuels, carbon analysis. And that CI ratchets down every year towards this 2030 goal. Fuels with CIs above the standard, the line here, generate deficits, and fuels with CIs below the standard generate credits. And of course, we plan to generate substantial credits with our manure-derived jet fuel. Next slide. This slide depicts some of the businesses on the left that sell fuels with CIs above the cap for their fuel type and must consequently purchase credits in order to reach compliance with this 20% goal. The examples on the right depict businesses that sell fuels with CIs below the cap that can sell credits. And I should point out here that fuels must be transported to California to qualify for LCFS credits, and jet fuel is easily transported to California from anywhere in the world to obtain these credits. Much easier than transporting gas and other materials. Next slide, please. Each fuel type has a range of carbon intensity scores as shown in this graph. Markers represent the CI score for certified fuel pathways, and the length of each bar represents the range of CI scores that can be achieved by each fuel type. So these CI scores are developed based on life cycle analysis, with scores that vary due to feedstock type, origin, raw material, processing efficiencies, fuel used in the transportation method, and the transportation method itself. Lower CI scores are more favorable because they are the cleanest life cycle solutions and therefore earn the highest LCFS credit values. So I've drawn in a forecasted CI value for FT jet fuel from dairy manure. You can see it there in the middle in green. It's about minus 410, and this is an estimate on our point because the pathway doesn't yet exist. But FT jet fuel is, like I mentioned before, is the cleanest burning jet fuel on the planet. And if you look at the CI standards on the right for FT diesel fuel, you see that it's positive 15 as compared to petroleum diesel fuel, which is somewhere right around plus 100. So the FT jet fuel can be produced from a variety of feedstocks. However, manure is the most carbon negative feedstock, as evidenced by this minus 287 carbon intensity in the bolded diamond for the bio-CNG category. So we believe that this FT jet fuel will have a CI of less than minus 400, producing the highest LCFS credits and the highest fuel sales of any transportation fuel in the LCFS system. Next slide. I'm sure most of you have seen this carbon cycle and biochar cycle depictions shown here, with roughly 50% of the pyrolysis carbon output going into the biochar product and 50% going into the syngas. It compels us to convert that 50% carbon in the syngas to its highest and best value end use. The carbon intensity of petroleum jet fuel is about positive 100, and the CI of our jet fuel, like I mentioned before, will be somewhere around minus 400. So burning manure-derived jet fuel removes about 4 times the greenhouse gas emissions that burning petroleum jet fuel adds. So that means that the net carbon drawdown of AWS manure-derived jet fuel as compared to petroleum jet fuel is about 500%. Next slide. So why is the AWS service solution unique? So first of all, we have an economically viable build, own, and operate solution for animal farms with a profit-sharing program for host sites to help drive profitability, shared profitability goals. We offer the most carbon negative and most profitable dual revenue solution from biochar production. We locate these micro biorefineries at the feedstock source, eliminating the highest cost of biofuels production, which is the transportation of the feedstock to the central plant. Our offtake products are energy dense, volume reduced, reducing offtake transportation costs and increasing market reach. Being permitted in South Coast means that we can be permitted basically anywhere. And our closed loop, zero waste micro biorefineries can be completely independent of utility company grids. AWS's graphene-based gas to liquid technology offers the highest conversion rates of syngas to jet fuel of any system known, with high automation in terms of running it and very low OPEX for the F2 jet fuel part of the equation. So the dairy model, this dairy model will work alongside current digester systems as well to convert that 50% of carbon that's still left behind for the farmer to deal with into jet fuel and biochar, solving a lot of the problems that the farmers typically have with the digestate. And a distributed micro biorefinery model works well for both large and small dairy clusters. Next slide, please. So that's it. Thank you very much for your time and attention, and I look forward to your questions and comments.
Okay, as the time is running, I propose to switch directly to the presentation from Laurent Bonnet. He's the General Director of Bionext, in charge of biofuel projects.
Okay, thank you, Michael. I will share my screen. Is it okay? Do you see my screen? Okay, so my name is Laurent Bournet. I am the General Director of Bionext. Bionext is the project society that has been funded by the partner of the Biofuel project in 2010. When this project started. And in this, the objective of this presentation is to make a status of this biofuel project today after more than 10 years of work. And to show you that it can be this technology developed within this project, it can be a solution to produce a sustainable aviation fuel. So the presentation will be in three parts. Of course, short presentation of the project, the presentation of the technology, the biofuel technology, and then the perspective in front of us. So the project, in a few words, the biofuel project, the objective is to develop a technology to convert the lignocellulosic biomass into advanced biofuels through the indirect thermochemical route. The other objective is to demonstrate this technology and commercialize a full BXTL chain. And the final objective of the project is to commercialize this technology and offer through a worldwide market of the process license. It will be brought to this market by Axens. And the objective is to bring to this market a fully integrated solution from the biomass to the final product. The main figure, you have it on the right part of this picture. The project is 11 years long. It started in 2010 and it is foreseen to finish this year, at the end of this year. The global budget is 190 million euro with some subsidies, more than 33 million euro, apart from the ADEME, and 3 million from Région Hauts-de-France and FEDER. One of the assets of this project is the partnership, which covers, I would say, from the field to the tank with Avril. It's a food processing group in France, who is working in the valorization in oilseed and protein, and into food, feed, but also green chemistry and also biofuels. And the tank, to the tank with Total, we will not present Total. Everyone knows one of the major energy company in the world. But also this partnership covers from the R&D to the final user. R&D work with IFP Energie Nouvelle and CEA, with also the licensing with Axens, but also the engineering phase with ThyssenKrupp Industrial Solution, with also the owner of the gasification technology. And finally, Total and Avril, who are, I would say, the end users of the process and on the product. So just now I switched to the presentation of this technology. So I will present the main step of this BXTL chain. The first step will be a pre-treatment of the lignocellulosic biomass by drying and torrefaction. So why do the consortium choose this pre-treatment by torrefaction? Because it was considered as a mild pre-treatment that fits to the requirement to the downstream unit. So the objective is to make the biomass more brittle by destroying hemicellulosic part mainly. And this biomass more brittle can be easily grinded, and the powder that is recovered fits with the requirement of the pneumatic transport system of the gasification step. Another advantage, and you can see in this picture, that we have several torrefiers for one gasifier. It enables also to have some supply of the biomass with a decentralized scheme, because torrefaction has main great advantages for this kind of scheme. You remove the water, you densify in terms of energy the biomass, and also you stabilize the biomass. It's hydrophobic, far less sensitive to bacteriological activities or degradation. So you can torrefy the biomass near to the resource and transport on a longer distance the torrefied biomass to a bigger gasifier to optimize the size of the plant. The gasification step is an untrained flow gasifier owned by TKS, ThyssenKrupp Industrial Solutions, sorry. It's the brain flow gasification process. So we are working at the right pressure to be in a position to send the syngas to the Fischer-Tropsch without any compression step, at high temperature and under pure oxygen to avoid nitrogen in the syngas. And with high temperature to have a very high carbon conversion of the biomass. The rate of the carbon conversion is in the range of 99.9%. So we avoid to have any issue with stars purification in the downstream unit. This was a choice of the consortium at the beginning to select this kind of technology for the chain. Then we have I would say, the block of syngas conditioning that is with a classic step, I would say. First, water gas shift to adjust the H2 to CO ratio up to the level optimum for the Fischer-Tropsch synthesis. And then we will have acid gas removal step when we will recover biogenic CO2 that can be valorized in food application, but also for sequestration, it can be also envisaged. Then we will have the final purification. It's a generic word for an enchainment of catalyst scavenger to remove all the impurities that fits the specification of the Fischer-Tropsch catalyst. And here we will use the Gazelle technology owned by Axens and put on the market by Axens. That is using it's a low temperature with a cobalt catalyst, and will orientate the production to the medium distillate. So we can choose through the upgrading and hydrocracking unit downstream the Fischer-Tropsch. The main product can be a diesel cut or biojet or advanced sustainable aviation fuel. So as a whole, this complex can be seen as a bioenergy hub, because you will introduce lignocellulosic biomass on one hand, and you can also introduce other type of feedstock fossil, but also plastic or waste wood, for example. And once it goes through the gasification step, you will convert it into syngas. You will recover green CO2, and you have a different opportunity for valorization of different products. You can choose to maximize green electricity production, but you can also valorize biogas, bio-LPG. You will have for road transportation gasoline or biodiesel, and sustainable aviation fuel. You have some flexibility in the range of production of each of these products, and you can also make biopetrochemical basis from Fischer-Tropsch product or bioloop basis. You can also introduce in the middle of the chain green hydrogen, because each molecule of hydrogen you will introduce, it's a water gas shift you will not convert. You will not convert a CO through the water gas shift, so you will save one molecule of CO2. So the addition of green hydrogen is has a great potential to increase the yield, the mass yield, and produce e-safe and introduce e-safe in the final product. So in a few words, and to summarize, in the biofuel project, we are now working for 10 years of R&D development, driven by international actors who are more or less leaders in their market and supported by the ADEME and the FEDER. As you have seen, the technology I have presented to you just before, we are talking about technologies that are today available at industrial scale, but on other applications. The gasification technology is working and has been proven by ThyssenKrupp in Puerto Llano in Spain at industrial scale in the EGCC plant, power plant from coal. So it has to be adapted to the biomass. The water gas shift, the syngas conditioning, we are using technologies that are available in the oil and gas industry, in the syngas purification world, and have to be also adapted to the impurity linked to the biomass and to the feedstock itself. So, and the Fischer-Tropsch, I would say, will be used as it is because the effort is in the purification step. So there is no development of the Fischer-Tropsch technology within the biofuel project. We will use as it is the Gazelle technology. And to prove this adaptation and to show and to give the data to be in a position to upscale this technology at to the biomass application, we will use the two demonstration units that I will present to you quickly on this picture. So here we are in Bonnet. We are 50 kilometers in the north of Paris, in a site that is owned by Avril. This is the torrefaction demo plant. So we have two demo plants, one dedicated to the torrefaction, the other dedicated to gasification and downstream part of the chain. So this is the torrefier and the dryer and the torrefier. The technology that is used is a multiple earth furnace. And you have the storage of the raw biomass, the storage of the torrefied biomass, and all the process of torrefaction. What has to be known is that we work in campaign, so we will use different kind of biomass. Sometimes it's wood, and we will use these cells here to introduce the wood chips into the process. Sometimes it will be straw. So for straw, we will store the straw bale in this part. And behind in this building, we have a pelletization step, and we torrefy the pellets of grassy biomass before torrefaction. And the range, the capacity of this unit, it's between 1 and 2 tons per hour of torrefied biomass. Now we switch to the Dunkerque demo plant. So Dunkerque is located in the top north of France, in a site owned by Total. And here we have the gasification step. So we will recover the torrefied biomass from Bonnet here in this installation. We will have a grinding step. Then we store the powder in these silos. Then the gasification step, and after the downstream unit and the Fischer-Tropsch that is in this part of the plant. I think yes, it's located here. You have the different section of the demo plant, and maybe you have noted that the Fischer-Tropsch is a very small bungalow when compared to the gasification, and it is to explain it in few words. Here, this plant is the use of this plant is to get the data for a safe scale up of the technology at industrial scale, and the minimum scale that is needed to prove the technology and to get this data depends of the operating condition, the maturity of the technology. And of course, if we are talking, for example, for the gasification part with more than 1000 degrees, you need a size that is representative to get a composition of the syngas that is and address the problem of the future industrial plant. So the size of the gasifier is between 10 and 15 megawatt thermic. That means more or less 2 tons per hour of torrefied biomass. And if we go in the downstream unit, we are now in operating conditions in mild temperature, 200 degrees. So we don't need that size to get relevant data. So for cost reason, but also for flexibility reason, the choice was to treat in the downstream section only a few parts, between 5 and 10% of the syngas that is produced at the outlet of the gasifier, and treat only this part. And to go to the end, the Fischer-Tropsch technology is used as it is. It is not developed, so it's just a pilot plant that is at the end of the plant of the demo plant. Okay, to go ahead, to summarize this, the strength of this technology. First, we want to prove full flexibility toward the feedstock with woody biomass, but also grassy biomass and energy crops when available. The other strength is the premium quality of the product, of the Fischer-Tropsch product, with an adaptation, an equilibrium of between the main product that can be changed through the upgrading of the Fischer-Tropsch waxes. So you can recover the renewable naphtha that can be a feedstock for petrochemical, for example, or you can produce also gasoline from this naphtha. The sustainable aviation fuel, so it has been certified and can be mixed up to 50% without any change in the supply chain, but also on the plane. And you can also have this renewable diesel with high quality, high cetane, low particles emission, and cold flow properties that perfectly fits the specification. The sustainability is also a very important point, because this BTL pathway is the one who is presenting one of the highest greenhouse gas emission reduction, higher than 90%, without CO2 sequestration. And now where we are in front of this biofuel project, so we can qualify a very promising results. We test different biomass on tools that are representative of the industrial scale, as you have seen in the picture. And it's so possible to address what is not common in the R&D world, to address the operational issues and optimization of the process with the real issues that will be present at industrial scale. We have performed more than 600 hours of gasification of pure biomass in Dunkirk, 1,300 hours of torrefaction in Bonnet, with the product quality that perfectly meets the specification of the grinding in Dunkirk. Last year we have produced some wax from biomass. So it's a global first, which validates the concept on the whole chain of this biofuel technology. So what are the next steps and the perspective? Of course, we have produced the first wax last year. The objective is to perform a global and a complete R&D program to validate the entire chain in the view of its industrialization. That means that we need some more hours of operation to validate and assess the aging of catalyst, of solvent, etc. And we optimize, of course, each step of the process, and also integrate each step of the process by exploring some recycle and so on. We also include the approach of e-biofuel, especially through the injection of renewable hydrogen. We want to consolidate the performance, implement the improvement from the operation feedback, secure the on-stream factor for long run, and clearly we enter in the commercialization step with some first contact and collaboration. And this commercialization will be supported by Axens on behalf of the consortium. It will be in front of the client, the single licensor of the complete big CL chain. So thank you for your attention.
Many thanks, Laurent, for this presentation. Paul, I don't know if all the panelists are there, or do you focus the question on the last presentation? Or do we have an open discussion on the overall topics? Of course, feel free to address your question for the last presentation.
Yes, Michael. I just had a look. We were hoping that maybe Neville and Freya would be able to come back, but it seems that their meeting must still be going on. So, in fact, we can take questions directly to you, Laurent. On peut prendre des questions directes. If the attendees would like to pass by the chat. There's a question there. I'm not sure if it's addressed to particularly. What would be your best level for an aviation target in 2030 for RED 3?
Yes, a question raised during the presentation from Bernard.
Yeah. So, would anybody like to raise a question directly to Laurent? So I maybe would like to ask a question, if I may. So we saw from the demonstration of biofuel here in France that there is the torrefaction unit in Bonnet, if that's correctly stated, and then with the gasification and Fischer-Tropsch unit established in Dunkirk. So when you're looking to roll this out through the licensing by Accents, what would be the ideal range? Because obviously the idea is to have a feedstock coming in from a certain circumference distance from the gasifying Fischer-Tropsch unit. So in order to achieve sustainability criteria, what would be the optimum? What would be the maximum range in terms of transport of the torrefied biomass?
Oh, it's a wide question. It's a good question. What we have seen through internal studies that it is highly dependent of the localization of the plant. Because, for example, if you are in France, if you are in Canada, the story is totally different. So the capacity to of course address this sustainability and not to transport for a too long distance the biomass to the plant. So the optimum size is totally different when considering the localization. It's also different considering what the final client is able to mobilize. Our target is to provide a technology that can treat woody biomass, grassy biomass. So if the final client is able to mobilize wood chips, but also wheat straw or rapeseed straw, of course, it will increase the potential of biomass that can be supplied in a reasonable collection radius around the plant. And then above that, you have also this decentralized scheme that can make sense. For example, if you can have a torrefaction unit near to a forest, but also near to fluvial transport, it can make it makes sense according to our study to collect the biomass around this torrefaction plant, transported by boats to the gasification unit, and increase like that the global collection radius when keeping, of course, the sustainability criteria.
Okay, thank you. That makes perfect sense. And I imagine that drives also your, or maybe it's the Accents part of the group that is commercializing this technology. And I imagine that logic is very much applied to the geographical markets that they will be looking to commercialize this technology to first. I imagine that's a key criteria in determining where to develop, where to commercialize this technology around the world. This question of availability of feedstock and volume of feedstock and the proximity.
Yes, and we come back also to the question of incentives. It will be also where the incentives will be in place and present and active for the advanced biofuel production.
Okay. And you say there are some first contacts. Would they be in Europe or would they be outside of Europe? A bit of both?
Both, yes. Both.
Okay. Good. Well, we wish you luck with this because it can make a difference.
And Paul and Laurent, what is important to remind also is today there is no or almost nothing on the mandate for the SAF. When you have some mandate on tax mechanisms or incentive mechanism for the road transportation fuel. So it's mandatory to have such a mechanism in place. Otherwise, the owner of the biomass, the operator, the producer, will be in favor to produce road fuel rather than SAF.
Yes, you're perfectly right. There is a discrepancy between the two routes today. On one side, we have something established, quite clear. And for the SAF, there is it's not that clear and not in place today.
Work in progress.
Yes.
Okay. So you say it's end of the year, it's going to be commissioned and fully operative.
It's fully operative today,
Okay.
the demonstration plant, but fully operative. We need time to perform and complete the test program.
Right. Okay. And that is scheduled to finish at the end of the year.
Yeah. The project is scheduled to finish at the end of the year.
I see. Okay. And overall, you're satisfied with how things are developed. It's 10 years. It's a lot of input. It's a lot of energy.
Yes.
You feel successful at this? Yeah, coming to the end of it. You feel successful? It sounds like it.
Yes, I hope it will be a success. Until we are not at the first industrial plant, the success for this kind of project will be the first industrial plant, of course.
Yeah.
So
yeah, I'm sure it's coming.
I hope.
I'd like to believe it. Yeah, me too. Okay, Michael, maybe you want to make some closing remarks. I can't see any other questions coming through currently, and I don't think Neville and Freya have been able to free themselves up to get back to us. So I think we can maybe have a closing remark if you'd like to.
Yes, thank you again for this afternoon. Is very interesting. And of course, it's important to remind that the growing pressure on the aviation sector to decarbonize its activity. So we need, as a customer, as a producer, as operator, as off-taker, to have a clear picture on the mandate. And we have discovered this afternoon many technical opportunity to reach this kind of objective. And it's clear that different pathways are on the table, and it's required to reach this net zero emission objective. So I'm sure, and I'm very enthusiastic in the fact that we are able to cope with this objective if the mandate and the policy are clearly defined, and we are not opposing some valorization of biomass, SAF versus road fuel, etc. And that's all for me. And again, thank you for this afternoon.
Thank you, everybody. Thank you, Michael. Thank you, Laurent. We very much appreciate your input, and thank you to all the participants. I'm sure we've all taken away some interesting information, and also the fact that the diversity of routes to achieving sustainable aviation fuels, as we saw this morning with marine biofuels, leads us to believe there's hope, and that there are ways to decarbonizing transport which are moving forward in the right direction, and we hope will accelerate and move faster in time with the right conditions from policy.